Hello, everyone. I'm Meg Rippey. I'm an assistant professor in civil and environmental engineering up at Virginia Tech, and I'm here today to talk to you about freshwater salinization, focusing on causes, consequences, and trends. And kind of in addition, to introducing sort of the problem space, focusing on kind of scope, scale, and why we should care. I'm also going to draw attention to the wickedness of freshwater salinization, and I promise I'll define that term a little bit later, and why it matters when we start to think about potential solutions and what we might do next, which I understand, is the focus of the rest of the week. And the other thing I want to emphasize is that this particular talk of the two-part series is going to stay intentionally broad. The next speaker, Stanley Grant, is going to provide a more detailed local example of freshwater salinization that has global implications. So when I say freshwater salinization, what exactly do I mean? Freshwater salinization refers to the process of increasing ion concentrations that can include things like sodium, chloride, calcium, magnesium, potassium, and sulfate, but also things like pH, alkalinity, and hardness in our nation's freshwaters over time. And as indicated, the causes are diverse, very regionally specific, and complex, which means, they're not always agreed upon. One of the big causes is road salts. It's probably why many of you are here today. About 20 million tons are applied each year in the US, and that releases sodium, chloride, calcium, and magnesium to local waterways. But there are many other causes as well: weathering of concrete, inputs of sewage, and animal wastes, lawn irrigation with recycling water, application of lawn fertilizers, use of water softeners and, in-home products, and many more potential causes, all of which have their own ion signatures and, other characteristics. So there's really a lot going on here. And I want to emphasize that the scale of the problem is really broad. So first, we're going to take kind of a continental US view here, looking at a map from a USGS assessment of trends in specific conductance, which is just a measure of salinity, from 1992 to 2012. And this is in 422 streams across the US. Anytime you've got an increasing trend, we've got an upwards red triangle. A decreasing trend is going to be that green triangle. And then kind of no trend is this open white circle. And you can see that salinization is increasing in many regions of this map, but particularly, along the East Coast here, including in Northern Virginia, which is where I am, right now. So zooming out a little bit further, this is not just, a US continental kind of problem. It is a global problem. And that's nicely kind of encapsulated by this graph from Sujay Kaushal, who spoke last time Winter Salt Week happened. And it's showing chloride concentration on the y-axis and then time on the x-axis. And there are a lot of different US streams on this map. Those are the ones that are indicated here in purple. But I want to draw your attention to these orange squares, which is the Seine River in France. It's one of the longest time series on this particular plot. And you can see it going from about 6 milligrams per liter chloride in the 1900s up to about 30 milligrams per liter closer to present time. So we can say that in the past 100 years or so, chloride concentrations have increased as much as 5-fold. So, a lot of these trends are also increasing upwards. So this is really, a global problem that we're seeing. Okay. So now let's talk a little bit about why we should care about freshwater salinization. And there's a lot of different reasons for this. And the first is that we care about the environment. So this particular graph that I'm showing here is from a wonderful study by James Roy, comparing chloride concentrations in groundwater and streams and benchmarking them relative to chronic aquatic life guidelines. So we've got from the US EPA, this 230 milligrams per liter chloride, that's the blue dash line. And then we also have Canada's standard here. So great to see you, Canada, 160 milligrams per liter on this plot as well. And just looking at, sort of the urban areas, we've got groundwater urban and surface water urban, we can see that we're often exceeding these chronic aquatic life guidelines, which indicates that those waters can be harmful to aquatic life. The median for groundwater is well above both thresholds, and the median for surface water is kind of nested in between them. Okay, so we should care about freshwater salinization because we care about aquatic life. Kind of reason one. We should also care about freshwater salinization because we care about, public health. In the state of Virginia and, many other states, there aren't drinking water thresholds for key ions like sodium that have public health implications. But the US EPA and the WHO do make recommendations that are intended to be protective of people on low sodium diets. So that's a value of about 20 milligrams per liter sodium. And then to be protective of drinking water taste, that's about, 30 to 60 milligrams per liter sodium. And we see these thresholds being exceeded in many drinking water systems nationally, but I just want to draw your attention to one example that you're going to be hearing about more in a little while. The Occoquan Reservoir in Northern Virginia. This reservoir is a major raw water source for Fairfax Water's Griffith treatment plant. That's that purple star here kind of on the map. That's the Occoquan Reservoir. And that treatment plant provides drinking water to around 1 million people. And what I want to draw your attention to is the panel on the right, which illustrates changes in sodium ion concentration over time. And most specifically, that purple line that indicates changes at Fairfax Water's intake. And you can see that really early on, sodium levels kind of fell below both the EPA's health advisory, so that's the dashed line, and the lower taste threshold, that's the solid line. But starting kind of in the late 90s, they began to exceed that health advisory, and in more recent years, the taste threshold as well. And that's really of concern to the water utility. So another reason we should care about freshwater salinization is we care about our infrastructure. Salt's what's known as hygroscopic, which means it absorbs water from the air, and that allows corrosion to occur at lower humidity levels and for longer periods of time than it otherwise would. Salt also increases the capacity of water to carry a current, which speeds up the corrosion process. And it's known that chloride, one of our problematic ions, can break down protective oxide layers that form on the surface of some metals. And the net result is we get corrosion. So this is, an image of corroded metal pipes that are used to convey water or wastewater. We also get corrosion in the metal components of our bridges and roads. And it's been estimated that replacing corroded infrastructure is a multi-billion-dollar proposition. So this is a really significant thing to think about when we're thinking about freshwater salinization. Another reason we should care about freshwater salinization is that we do not want to have to desalinate our fresh water in order to drink it. I can't emphasize this enough, and it's not as far-fetched as we might believe. I mentioned earlier that salinization is a real concern for water utilities like Fairfax Water, and they actually went out and estimated what the cost of desalinating fresh water at the drinking water treatment plant might be, and determined, really conservatively, that the cost would be over $1 billion. And that would represent a huge economic burden passed on to ratepayers, as well as this source of cognitive dissonance, desalinate fresh water, and we'd really rather not go there. Okay. So now that I've kind of introduced you to freshwater salinization, the scope, the scale, and kind of why we should care, I want to talk a little bit about this wicked problem idea and why I think the freshwater salinization syndrome qualifies. So wicked problems, first and foremost, aren't evil problems. They're a class of societal challenges that are characterized by deep uncertainty, contested values, and complex interdependencies that span social, ecological, and our technological systems. Wicked problems don't have a single agreed upon problem definition or solution, and attempts to intervene actually have the potential to reshape the problem itself, generating new feedbacks, trade-offs, and unintended consequences. And I've listed on this slide a variety of characteristics, that are generally accepted for wicked problems. And I just want to focus on, one of these today, kind of for time, that has particular, implications, I think, for freshwater salinization and what makes freshwater salinization wicked. And it's the fact that stakeholders often have very different worldviews and frames for understanding wicked problems that make them difficult to characterize and solve. Okay. And that's what I'm trying to emphasize here, on this slide. I'm highlighting some quotes from stakeholders that capture different perspectives about freshwater salinization, focusing on consequences and causes. Kind of the top two sets of quotes are drawing attention to different perspectives about salinization's impact on aquatic life and infrastructure. And of course, if we have different opinions about what matters, we may focus on different ions, we may focus on different timescales, and that can lend itself to different management strategies. And now the bottom set of quotes is focusing more on contested causes. Everything in the detergent aisle is salty. It's going to be heading to the sewage treatment plant, and those salts will wind up in our drinking water. That's one perspective. And then the other one is most of the problem is private sector de-icer use. It's just not regulated. And of course, if you think the main cause of freshwater salinization is product uses in homes, you're going to advocate for a very different set of interventions than someone who feels that the major problem is private sector de-icer use. So these different viewpoints and contested values kind of combined with the complexities and uncertainties, associated with freshwater salinization, they're a real big part of what makes it wicked, and difficult to solve. So, why might wickedness matter, as we push towards solutions? I feel that recognizing freshwater salinization as a wicked problem really does have important implications for how we approach it. Wicked problems, aren't solved in the conventional sense. They're managed through iterative, adaptive, and participatory processes that acknowledge contested values. And that really requires innovative approaches that help facilitate shared learning across all the actors. There are approaches that clarify how different actors view freshwater salinization, how those views shape our perceptions of risks and our solutions, and where the opportunities exist for aligning our priorities and making some meaningful change. And if we accept that freshwater salinization is a wicked problem, then we must also accept that our ability to address it depends, not only on biophysical understanding, which is critical, but on our collective understanding of divergent values and, perceptions about freshwater salinization, about that biophysical understanding, and why they differ. My soapbox, if I had to stand on, would be that wicked problems require bottom-up convergent approaches for problem solving and salt management, and we need to work together, to help solve these. And I'm sure you'll be hearing a lot about some of those different solutions the rest of the week. So just to summarize and conclude, I hope I've convinced you that freshwater salinization is this global challenge with diverse causes and consequences that are regionally specific and complex, and ergo not always agreed upon. That freshwater salinization also has many elements of a wicked problem, including these contested values, kind of in the context of its complexity and its uncertainty, and that has implications for how we work together to address it. Collaborative, iterative, adaptive, and participatory processes are really needed that help us acknowledge and address some of these contested values. And with that, thank you, and I'll hold questions to the end, after Stan has presented.
Thank you, Megan. So please do feel free to go ahead and type questions into the chat, and then when Stan's done, we'll take questions for both of the speakers.
Oh, thank you.
Stan, that's good.
Great. And I think you can hear me okay, right? Excellent. Okay, so my name is Stanley Grant. I'm a professor of civil and environmental engineering at Virginia Tech as well, and director of the Occoquan Watershed Monitoring Laboratory up here in Northern Virginia. And Allison, I have to say, you picked a really sort of opportune time to have the Salt Wise Week, because we've got a lot of de-icers on the road today, I can tell you. And thanks again for inviting both of us, and really appreciate Meg's presentation kind of teeing up this next piece. So I wanted to do a deeper dive into the causes of drinking water salinization. That was kind of one of the two kind of endpoints that Meg mentioned, with a little bit of a toe in the water into the sort of ecological impacts too, but primarily focusing on drinking water salinization. And here's my outline. So I wanted to focus specifically on rising salinity in the Occoquan Reservoir, talk a little bit about a National Science Foundation project that I led that really kind of got at what Meg was talking about, that is that convergent, kind of stakeholder-driven, bottom-up approach to addressing the salt pollution problem. What we found, and then maybe focus a bit specifically on road salt, and then next steps that we're taking in terms of kind of getting the message out there and creating tools that people can use to better understand the problem. Okay, so rising salinity in the Occoquan Reservoir. So this is a reservoir in Northern Virginia that is a source of drinking water for up to 1 million people. And basically what you're seeing on the left here is the Occoquan watershed, which is adjacent to the Potomac River. And basically that watershed drains to a reservoir called the Occoquan Reservoir. And at the base of the reservoir, as shown in the picture, there's a dam, and the Griffith drinking water treatment plant pulls water from that dam and then basically treats it and then sends it to retail and wholesale customers in the region. And so basically, this is interesting. This particular site is interesting because it's one of the first and largest quote unquote one water systems in the United States. And what I mean by that is that the water that comes into that reservoir doesn't just consist of sort of watershed inflows, from streams, as you see there, the various watersheds. It also receives urban runoff from some pretty developed areas of the watershed that we'll see in a minute. And it also receives inflow from reclaimed water or treated sewage that flows into Bull Run there and ultimately into the Occoquan Reservoir. So it's really got three different sources of water, which basically on the upside makes it very resilient to drought, which is fantastic. But not on the downside, but one of the challenges that we face is that we have that overprinting of a lot of different salt sources, which can create some water quality challenges. And in fact, I think Meg kind of showed a version of this figure. This is the concentration of sodium in the finished drinking water from Griffith Drinking Water Treatment Plant over the last 40 plus years. And you can basically see that it started out in the 80s and 90s, kind of within that band of below 20 milligrams per liter, which is great. And then it's been slowly climbing over time. And in fact, when I first got here in 2018, I went to the general manager and I asked, what keeps you up at night? No mention of PFAS. At that time, it was basically this rising trend in salinity, not because these concentrations are particularly high at the moment, but because the trend could basically take the water utility to places it didn't want to go. So that kind of led to writing a proposal to the NSF and their convergence research project or program. And we were successful. We got a 5-year project out of that. And we brought together about 100 people, scientists with biophysical training, social scientists, with kind of looking at the governance side of the problem, and then a very, very deep stakeholder team of water utilities and agencies and so on, who are basically trying to engage in this salt issue and try to address it in the Occoquan Reservoir. And we call this our squid of convergence. Basically, the idea was that these threads would kind of move kind of more and more closely together over time as we addressed various sources of salt in the reservoir, including wastewater and then also salinization from de-icers and so on in the watershed. And I think that actually happened. I think that's a fair kind of characterization of what actually happened, in fact. One of the things that I would say about this is, we had a lot of folks involved, and so we produced a lot of scholarship, publish or perish. But one of the things that I'm really proud of is that we have a paper coming out in one of the Nature portfolio journals, which basically summarizes kind of what we found in terms of the key sources. And there's a QR code there if you want to link up to the article. It's kind of a preprint form, but coming out, I think, in February. To basically, talk about these issues with respect to what's driving freshwater salinization in this particular reservoir as an example that could be internationally interesting. And again, the co-authors kind of reflect this really diverse approach where we've got researchers, we've got folks from the water utilities and the wastewater utilities, and then we've got social scientists, and we also even have Prince William Conservation Alliance, Ashley Holmes, so basically community organizations as well. So we try to get a lot of diverse voices engaged. And here's kind of a summary of those results in a pictogram form. So basically, we were concerned about rising sodium in the drinking water. That was kind of our target. And what we found was that there were 3 major sources. One was obviously road salt. That wasn't a big surprise, but we did find that each of these have different kind of seasonal patterns. So the road salt impacts on the drinking water tended to show up in the winter, as you'd expect. We can see spikes in salinity in the runoff in the watershed, and those propagate all the way through the drinking water intake and then into the finished drinking water. So definitely a one-to-one connection between what's being applied on the road and then what we're drinking a couple of weeks later. Interestingly enough, we also saw a strong signal from the reclaimed water activity, but this tended to kind of show up in the summer when the dilution from other inflows from the watershed were lower because of higher evapotranspiration, more of the water going into the atmosphere. Basically, less of that reclaimed water was being diluted with less watershed inflow, and the net result was it was contributing higher sodium concentrations. I guess one of the big surprises, at least for me, was that the treatment chemicals added at the drinking water treatment plant are also a big part of that story. In fact, during the summer, the water utility adds up to a small elephant's worth of sodium hydroxide a day to basically prevent corrosion of the distribution system. So it's an extremely important activity. But we actually then traced why it is that they have to add so much chemicals, and it's really a fascinating story, having as much to do with ecological processes occurring in the reservoir as acidity generated during the treatment process. So basically, three main sources of salt contribute this signal and different seasonal patterns. And then basically thinking about I'm not supposed to talk about solutions, but really thinking about kind of innovative governance approaches to address that. And for some reason, framework became framework. So I guess maybe we can cook with it too. But anyway, that's kind of the pictogram. I'm going to focus on road salt specifically because I think there's a lot of interest in that story here. So what do we know about drinking water salinity and road salt? Well, here's a map of imperviousness basically spreading over that Occoquan watershed over time. And if you know any microbiology, you've seen colonies growing on petri dishes, and it's kind of a pretty strong analogy between the growth and imperviousness that we see in the watershed. It's not hard to imagine where this is going to end up over time. And what's kind of interesting is that if you look at that imperviousness, we have monitoring stations throughout the watershed for the past 40 years. So these are kind of natural experiments where some of the subwatersheds that we're monitoring had a lot of increased imperviousness. That's the color basically indicating when the imperviousness was added. And then adjacent, subsheds would have very little imperviousness added until maybe really very recently. That those kind of red dots, if you can see that, indicate recent imperviousness. So because we have these long time series, we can start teasing out, what's the minimum imperviousness at which we see signals, and what happens over time as higher imperviousness, contributes more and more salinity. And so let's start with the subshed, which had very little development. What we see basically there, and what we're showing in this top plot, is impervious area over time starts out kind of a little above 1%, and then it rises at the end of the 40-year time series here to just a little over 3%. And what you see in this bulk salinity is there were occasionally really big spikes. We have no idea what was causing those, but overall, the bulk salinity was pretty low, kind of reflecting geogenic background levels, until we got to about 2 to 3%, at which point we start seeing a consistent rise year on year in the salinity. What you're seeing in color here is the stream temperature. What's really fascinating to me is that in this particular watershed, maybe because those residentials are new development, that imperviousness is new residential development, and a lot of that de-icer that is applied is basically stored in green stormwater infrastructure and then later released to the stream. The salt's actually coming out in the summer, not in the winter. So that's really kind of fascinating. And then we can move next door to a watershed that was really highly developed. So this is over 30% imperviousness over that 40 or 50 year time series. In fact, Dulles Airport's kind of up here to orient you. And you can basically see the scale is hugely different. Now we're talking about bulk salinities rising up over 2,000 microsiemens per centimeter. Most of those salinity peaks are occurring during the winter, during cold weather. That's the blue colors. So we see the extremes are increasing over time, and we also see the baseline concentrations are increasing over time. So basically, is sort of looking at the evolution of the salinity signal in response to kind of what happens with the imperviousness. So, there's a lot more to that story. And again, some of these papers that I mentioned kind of get into it. But I wanted to tease you with a little bit of kind of our looking forward, which is in terms of thinking about taking all this data and all this knowledge and creating interactive modeling tools for planning, communication, and education. And one of these was published this year in the Journal of Water Research. And there's another QR code you can click on to get some more details on that, but basically the idea is that we want to create models of these complex systems which are physically accurate, so they don't ignore the physics and the biology if there's biology going on, but at the same time are simple enough to operate interactively and get sort of answers in real time or even forecasts. And so the way we do that is we draw a control volume, for example, around the reservoir, and we analyze not only the inputs of water and salt over time, but also the age of that water as it moves through and then out into, say, the drinking water intake. And that information allows us to create hourly to daily time series of predicted sodium, chloride, nitrate, and other contaminants, including PFAS. We're using this same model for PFAS. And just to give you an idea of how accurate these models can be, here's a time series for a 10-year, more than 10-year period, daily time series of sodium, chloride, and nitrate. And the measured data are the blue dots there, and the predicted model is in black. You say, well, okay, well, you can do that with pretty much any sophisticated model. But the cool thing is we can do this in real time. So, and I wanted to show you an example of that. We have another paper in second review with Water Research, which is basically applying that same approach for a small catchment, looking at de-icer application in the catchment, accounting for flow paths through the watershed, including engineered storm drain systems, the vadose and groundwater, and basically using that information to reconstruct what the salinity signal should be. And so this particular study, we're looking at Flat Lake Branch, which is a small watershed that drains ultimately to the Occoquan Reservoir, so it's within the Occoquan watershed. About 20,000 residents live there. 95% classified of the land use is classified as developed land cover, but a lot of that is developed open space, and 40% of it is low intensity development. So it's a relatively highly developed but relatively disconnected watershed with a fair number of residential houses. So basically, we used our model to reconstruct a daily time series of chloride concentration, shown here on the vertical axis, over 10 years. And the measured data are in sort of dashed there. We basically took hourly specific conductance data and converted it to chloride. And then the model is the solid line there. You can kind of blow up in the validation period what's going on. And we can see the solid line is the model prediction, the dashed line are the measurements, and we're capturing most of the big de-icing events, as well as the transition from kind of wintertime highs to summertime lows in that. One of the cool things that comes out of this effort is we can infer exactly how much de-icer was applied. So we now know for this, on average, but it varied year to year, of course, that 206 metric tons of de-icer chloride was deposited per year. And because we know how many people were in the watershed, that works out to about 30 grams of chloride per person per year. But of course, most of that de-icer is applied during the winter in these big boluses, which result in these really large de-icer kind of wash-off events in the winter. And so if we have time, Allison, I've got an example of that that I wanted to play with interactively, but you let me know if we've got a moment to show that.
So you got a minute.
Okay, I can do 1 minute.
If you want to go.
Yeah. So here's the chloride concentration. Again, the dots are measurements, and this is time for 10 years measured in days. and basically, the dots are measurements. The model is the orange, and basically, this is what model, was sort of optimized to the data to get that 206 metric tons of chloride per year. So we might ask a question, well, what if we cut the de-icer use in half, right? So we set a sort of a goal for each of the residents in the watershed to reduce their de-icer use by half. What would happen? Well, if we did that, basically, when I'm showing also the 230 milligram per liter criteria, that kind of horizontal orange line there, basically what would happen is that except for the worst winters, we would be now below that criteria. Conversely, we can say, well, what if residents doubled their de-icer use? Well, then in that case, basically every single winter, with one exception, we would have concentrations over that 230 level. So anyway, the idea here is that because it is interactive, we can play games, we can deploy it in kind of a dashboard frame, that it might be useful ultimately for kind of getting the word out there, setting targets, and forecasting. And so with that, I'm going to basically stop and just say thank you very much. And I think both Meg and I would be delighted to answer any questions you might have.
Thank you. Yeah, thank you both. I could definitely see a future webinar, Stan, where we have you come back on and can play around with that model quite a bit more. But we do have a lot of questions, so I want to jump into those. And of course, if anybody has to pop off, since we're at 1 o'clock Central Time, 2 on the East Coast, this webinar will remain available on YouTube at this same streaming link. So don't worry, we're not going anywhere. But I will try to share some of the questions that we had. There were several about the relative contributions of different sources into the causes of this problem. So both talked about isn't road salt number one? What about sea level rise? That's not our biggest concern here in Wisconsin. Also, when we have new construction, disturbing soils, causing more leaching. So do you guys want to talk a little bit about the relative kind of contributions of some of the different sources?
I'm going to pass that one to you, Stan, since you have nice pie charts and framings that you can talk about that from.
Yeah, no, I mean, I think that Allison, you hit the nail on the head when you introduced, this set of talks, and you said that the salt issue is really a local problem. And so I think that mixture of sources is going to be highly local. So if you're near the coast and you're sort of experiencing sea level rise, and seawater intrusion into your groundwater, and you're relying on groundwater wells, then clearly, seawater intrusion is going to be, the major factor. Or that can also occur in, waterways that connect to the ocean, obviously, and sort of intrusion of seawater, and that's happening on all the coasts, really. And so that is a huge issue for a lot of communities. And then, with respect to road de-icers, yeah, absolutely. In northern climates, we're using road de-icers. And what we're seeing, at least in the Occoquan, is that a lot of those are washed out of the reservoir, as well as probably, to some extent anyway, the groundwater over the rainy seasons that we have here in the summer. And what happens is that there's kind of a transition, that basically those really big spikes that you see in the winter due to de-icer wash off become replaced with kind of a lower creep in the salinity that's driven by other processes. For example, in our case, reclaimed water. And then, of course, we have layering on top of that what the water utilities are doing. And absolutely, soil disturbance is an issue. There's, corrosion and weathering of concrete in urban settings that is an issue. Really, all of the different kind of sources that Meg outlined a little bit earlier, I think. But the mixture is going to be very locally dependent.
Thank you. Yeah, and someone just asked, are there regional breakdowns in this? So I think I'd really encourage people to kind of go to your more kind of local or state, maybe environmental agency. I know Minnesota Pollution Control Agency has a salt budget for the state of Minnesota. So you can at least get a little bit more local for some of that information. So then there was another question about, I say for our scientists here, so I'll just read this. Economic implications of US policy is strongly biased towards economic costs versus environmental impacts. Is it up to scientists to be more clear and affirmative regarding the loss of ecosystems?
Yeah, Meg, do you want to take that, or do you want maybe you go first? I'll go second.
I mean, I guess what I would say is I think as educators, sort of in our realm as educators of science, I do think it's important that we talk more about the consequences and the impacts of the various interventions that we make, and that can be a lot of that is unintended consequences. And so when you think about the story of our infrastructure and the story of urban development is a story of good intentions and unintended consequences that we're still struggling to manage and even identify, in some cases. And I do think, that talking about those and having clear, communication about them is a job for science, and particularly for people who have an educational role in science.
Yeah, and I guess I would add that that our National Science Foundation project was focused very specifically on drinking water. We wanted to have a very narrow target to really begin that dialogue and allow people to self-organize around kind of what the future is going to look like, while being absolutely cognizant of the environmental impacts too. I mean, as you are well aware, a lot of the road salt issue, at least locally, is rock salt. It's sodium chloride, and so if we're looking at sodium in the reservoir rising over time, we're seeing spikes of sodium coming in from de-ice or wash off. There's a flip side of that, which is chloride, and the chloride is having really significant impacts on the benthic invertebrate communities in these streams. And in fact, we have, I think, one of the first chloride TMDLs in Accotank Creek within Fairfax County, very close to the Occoquan Reservoir. So I think all of the stakeholders were extremely acutely aware of the environmental ecological impacts, but they also saw the drinking water impacts as kind of part of that overall story.
And that kind of brings me back. I'm trying to skim through here all the other questions that came in. Someone said, there's a lot of talk about sodium. I'm not hearing about chlorides. It's always been my understanding that chlorides were the more important of the two. So I would say definitely in Wisconsin, we talk more about chloride. I think my understanding is that historically that's what has been studied more, right? Because chloride moves more readily like through the soil column. So we think it's going to show up in our groundwater, right? And sodium does bind a lot more to soil. Would you guys say that's kind of why people focus more on chloride when we're talking about road salt? I asked you guys to talk about, drinking water and like human health. And so maybe you focus a little bit more on sodium, but do you want to kind of expand on that?
I think it's really key to the end member that you're interested in too. So from an aquatic life standpoint, chloride, looms large, with aquatic toxicity. It would also, have implications, for certain vegetation, though bulk salinity and osmotic stress is, equally important there. When you're talking about public health, it is going to lean, more towards discussion of sodium. If you're talking about corrosion, it might be sulfates and chlorides. And in some cases, to avoid, like Sam was talking, to avoid corrosion, you might add, sodium complexed with, other things. So it can be really complicated. It's like add salts to reduce corrosion, add salts causing corrosion. It really depends, on the ions and on the context, I would say.
And we do have quite a few questions kind of coming in about what should we be using on our roads and our sidewalks. And I'm telling most of the attendees that we'll hit more of that later on in the week. But yeah, just one more came in here. Do you have info on salt use to suppress dust on gravel roads in the summer? So I don't know if you guys want to just kind of punt on that. Yeah, that's kind of what I was thinking. I'm just thinking, I mean, maybe not in more urban right parts of Virginia, but in more rural areas, that might be the case. I know Wisconsin, actually, because we're the dairy state, we've actually paved most of the roads in the state. And we don't, even more rural parts of Wisconsin have a lot of pavement. So the big milk trucks could get out there every day of the year. But in our neighboring states, Minnesota, Iowa, Michigan, a lot more gravel. And we do see calcium chloride utilized in the summer months as a dust suppressant, right? Like Maggie said, it absorbs water, brings water down to the road, and yeah, that's good to cut the dust. I don't personally have kind of rate recommendations on that. Unlike with road salt, a lot of rate recommendations. There's a lot of information that's been published that we'll be, getting to later on in the week, and happy to direct people to sources for that. There's a question here that I think will be more up your alley. Doesn't sodium contribute to soil compaction that then reduces permeability and infiltration?
Absolutely, and there's evidence that is happening as well. So that would be kind of added to the list of potential problems. So the structure of the soils, which affects the hydrology, which in turn affects pretty much everything downstream. So absolutely.
All right.
Yeah, we see that in our infrastructure as well, thinking about green stormwater infrastructure. I led a little project that was looking at that, trying to understand, what the impacts of salt on some of that infrastructure were. And we definitely do see, some impacts in that regard.
Yeah, and speaking of that, there was somebody who was interested in your work around native plants. So again, maybe we'll have you back on later for another webinar, just getting deep into that. But thank you so much today for coming on and kind of kicking off the week and talking big picture about this problem. We have folks from all across the country join in live, and my hope is that they will continue to share this with their networks, their friends and family and coworkers, and we'll just continue to get the word out. So I'm going to end the live stream for today. I'm happy to take any questions or comments that people have, or if you want to email me directly at wisaltwise@gmail.com. I can pass them along to Stan and Meg. But thank you all so much for being here. We do have, I will forward the question about how does road salt interact with micro and nanoplastics, and maybe we can take that on a little later. And I can actually send your answer out in the email with tomorrow's information. But thank you so much, everybody, and happy Winter Salt Week. Stay warm, stay cozy out there.
Thank you, Allison. Thanks
Yeah,
very
thank
much.
you.